Hello and welcome to this course, Linear Algebra 1. I'm Michael and I'll be taking you through this course. Alright, as a prerequisite to this course, you need knowledge of abstract algebra, and abstract algebra will introduce you to the basics of algebra, as representations in algebra, symbols that we use in algebra, and we'll tell you about properties of some structures and some binary operations, introduce you to things like associativity, commutativity, and the likes. Okay, and linear algebra is basically a study of vectors and vector spaces, and here's the outline for the course. So we'll be studying vectors and then vector spaces and matrices, and application of matrices to linear equations. We'll also be considering linear mappings, and under vectors we'll consider representation of vectors, operation on vectors, examples of vectors, and properties of vectors. Alright, so let's begin. Vectors and representation of vectors. So in elementary physics, a vector is a physical quantity that can be represented in terms of its magnitude and direction, and such vectors are often represented graphically by an arrow whose length in a given scale of measurement corresponds to the magnitude of the quantity, while its angular orientation corresponds to the direction of the quantity. Now, examples of vectors in physics: we have force, we have momentum, have velocity, have acceleration, and we know that whenever we are specifying any of these quantities, we also need to talk about the direction. And weight, for example, is a vector quantity, and we know that weight always acts downwards. That's the direction of the vector. And so, talking about representing these vectors, which we know from physics. For example, you may be told that you have a force acting towards the right, and the force has a magnitude of 5 newtons. And usually, when we represent this, you will know that this angle is 0 degrees. And so we could also have another vector acting in the same direction, another force, and say this vector has magnitude of 10 newton. It's also acting in 0 direction, that's 0 degree, that's towards the right. So you notice that the length of this line, of this arrow, is twice this, roughly twice this, because the magnitude of this vector is twice this one. So we use a scale of measurement, right, to represent the magnitude of the vector, while the orientation of the arrow tells us the direction of the vector. So for example, I could have another vector, say also of 5 newtons, but acting in this direction. Now, the angle this makes with the horizontal, say maybe 40 degrees, right? So specifying this vector has a magnitude of 5 newton and it's acting in direction 40 degrees. We know on the axis or the plane, we count the direction, angular direction, anti-clockwise, actually, right? So this is 0 degrees, this is 90 degrees, this is 180 degrees, I have 270 degrees, and by the time you come back here, it's also 360 degrees. Okay, so this is how we represent these vectors, right? However, in this course, we'll study vectors by looking at a tuple of scalars. And a tuple just simply means a collection, an ordered collection, right? As an ordered collection of scalars, especially those of Kn, where K is a field and N is a natural number. Now I'll come back to what a field is, which I believe, however, that which I think you should have been introduced to in abstract algebra. But however, I'll summarize properties of a field again. And so we said that a vector, a typical vector, which is an element of, say, Rn, or yes, it's a vector. So R, first of all, what is R? What is R? You know that R is a set of real numbers. Set of real numbers takes values from minus infinity to infinity, right? That's a set of real numbers. So in this course, we'll work with the field we'll be working with mostly is R. So what this means is that any element in R is a scalar. 2 is an element of R. 0.5 is an element of R. 1/3 is an element of R. So all of these are scalars. They are all elements of R. But let's look again at what a field is. Now I've said that R is a field. What exactly is a field? Now, looking at a field. So a field, which I'll represent like this: F, comma, plus, comma, dot, is made up of a set, a non-empty set. So F is a non-empty set. Non-empty set with two binary operations defined. Two binary operations. So the two binary operations here are addition and multiplication. I know what a binary operation is: an operation that takes two operands. So you have something here operating on another thing here to give you a result. It's a binary operation. So you have a non-empty set and two binary operations defined on the set. Now, not only do you have a set and these two binary operations defined on the set, and those two binary operations are usually addition and multiplication, but you also have a set of axioms that must be satisfied by a field. Axioms that must be satisfied. Axioms that must be satisfied by any set and a pair of binary operations that will form a field. So for addition, the axioms to be satisfied include one, closure. What is closure? Well, closure is usually implied. It's implied most times. In some texts, closure may not be included as a property, because when you say the operation is defined on a set, we infer that it is closed. But what closure means is that if you take any two elements, say A and B in F, and operate them under addition, that's A plus B, right? It must give you a result that is also in F. A result that is also in F. So all these properties are, say, for A, B, C in F, right? So closure, this is closure property. So another property, another axiom that must be satisfied by this set is that of associativity. So associativity says that when you are taking three elements, the order in which you operate them is not important. So I could have this. So I could add A and B first and then add the result to C, or add B plus C first and then add the result to A, but it must give me the same result, right? So if it gives me the same result, then addition is associative on this set. So since it gives me the same result, I can write either of them simply as A plus B plus C. So another axiom to be satisfied is that of the zero element. So there must exist an element 0. There exists an element 0 such that for any element a in the field, a plus 0 will equal to 0 plus a, and to give you a once again. So when you operate any element on 0, it leaves the element unchanged. So that 0 element must be part of the elements in the field. Then 4, you have the additive inverse. So sorry. So we have the additive inverse. So it says that there exists for every a, there exists another element which will denote minus a, such that when you add a to minus a, or add minus a to a, you will get the 0 element. So every element must have its own additive inverse, like this. And finally, I have commutativity. Commutativity says if you take any two elements, a plus b, it should give you the same result as b plus a. So the order in which you arrange them is unimportant. So there are also axioms to be satisfied by the set under multiplication if that set will be called a field. So under multiplication, we have once again a closure property. So it says that if you pick any a and b and multiply them together, their results must also be an element of F. And then associativity also holds under multiplication. So if I have any three set of elements, so the order in which I multiply them will not affect the result, right? And so I can simply write it as a dot b dot c. And then we have an element which we call the identity element. So this axiom is the identity axiom. Identity. So this says that there exists an element which we denote 1, such that a dot 1 multiplied by 1 dot a must give us a once again, and this time we are dealing with multiplication. So that element 1 is an identity element. And then for a field, we must also have inverse elements under multiplication. So inverse, so we'll call this the multiplicative inverse. So every element a must have an element which we denote 1 over a also in that same set, such that a times 1 over a must be equal to 1 over a times a, and must give us the identity element 1. However, there is a condition that must be satisfied, and that is that a must not be equal to 0. So every non-zero element in the set must have an inverse. Now we do not stop there. If F will be a field, then multiplication must also be commutative. Multiplication must also be commutative. So let me call this commutativity. So if you have a dot b for any a and b, a times b must also be equal to b times a. Then last set of properties we call distributivity. So distributivity says that multiplication distributes over addition. So if I have A multiplying B plus C, it is the same as evaluating A times B then plus A times C, and it happens from the left as it happens from the right. So this would also be A dot C plus B dot C. Alright, so these are the properties of a field. So like I said earlier, any element from a field like this is called a scalar, and then when you pick certain scalars and put them together, you have a vector. When you pick certain scalars and put them together, that's you form a tuple, you have a vector. Now R is not the only field that we know. There are several other fields, but some of the ones that you easily recognize. So I mentioned R, set of real numbers. Then you also have C, which is the set of complex numbers. Remember, the complex numbers are numbers of the form A plus bi, where I is the square root of -1, right? So these are fields. They are both fields. So when you pick any of elements like this and put them together, you have a vector. Now remember we talked about k raised power n, and we said k is any field. So for example, r raised power n, you can have c raised power n. So when you look at r raised power n, r raised power 2, r raised power n, and we said n is an element of the set of natural numbers. The set of natural numbers are all positive whole numbers starting from 1. So you have 1, 2, 3, 1, 2, 3, and so on. Keeps going to infinity. So when we talk about R1, you can have Rn, you can have R1 is just R, right? So you can have R2, you can have R3, and so on. So how does, and these are sets, so how does an element in R look like? That's the regular numbers we have. Any number, any whole number, fraction, decimal, rational number, or irrational number is an element in R. But how do elements in R2 look like? So R2 is a set of elements of the form A, B. Each element in R2 is made up of two scalars, A, B. So where A and B are elements of R, right? So examples of this, you have -1, 0, you have 2, 1/3, you have -2, -1, and so on. Also, what does an element in R3 look like? An element in R3 looks like this. Set of all A, B, C, such that A, B, and C are elements of R. So when you see R3, you are saying you have 3 copies of R. So now each of these like this are vectors, right? So for the case for this course, so those are vectors, right? Very good. And so this is a basic introduction to vectors, right? Now we can write these tuples of scalars in different forms, right? So when it's lying flat like this, a row vector, we call it a row vector, and when it's standing straight like this, we call it a column vector, right? So a column vector, you can have this row vector written as a column vector. So -1, 2, 1, right? Here it's a column vector. Then we can also write it as a row vector, where it's -1, 2, 1. There is a row vector. vector. Now, what's the relationship between this kind of vectors and the vectors in physics? Remember that when you are when you want to carry out operations on vectors in physics, you can consider a vector in physics as emanating from a particular origin 0, 0, right? So when you draw a vector like this, okay, let's make it come from the origin, right? So when you consider a vector, you could have a vector like this and then call it A. Could have another vector from that one to this point. I'll call this one B, right? So usually this vector we can this is the x-axis and this is the y-axis. So this vector can be drawn by moving a particular distance to the x-axis and a particular distance to the y-axis. So say you're moving 2 units to this point in the x-axis and then you're moving 3 units in the y direction, right? And so that means that I can come here and just call this 2, 3, right? And so for this particular vector B, so you move from the origin, you move say 3 units to the y direction, y-axis, and then you move say 7 units in the x-axis. So this vector would be 7, 3, right? 7, 3. So that's the end. Okay. Do I represent this? Good. Okay. So this values here represent the end point of the vectors, right? The end point of the vectors. So you can pick, you can take numbers from the x-axis and the y-axis to indicate the end point of these vectors, right? And so if the end point of every vector can be identified uniquely by these points, that's the end point of the vectors can be represented by these points, right? So you see that you can represent these vectors by these numbers. However, these vectors, remember, can be expressed in terms of magnitude and then direction as well, right? So okay, so alright, so that's on the introduction to vectors. Thank you, and see you in the next video.